Hey guys, I hope you are doing good. This is lecture 5.3, the last one of lecture 5. We'll be speaking about P2P applications. I think you're very close to that. Um, but then let's get started with this. So P2P applications are basically a peer-to-peer architecture as a whole is an architecture where you have no servers. So you do not have, as opposed to the client server one, right? You do not have a server that is the sole source of data. Everyone in a peer-to-peer application, anyone in the peer-to-peer architecture has data to communicate, right? So all the peers are servers depending on who is sending or who is receiving, right? So it's very nice because it's very scalable, right? Since each and every pair can be a server or a client, so there's no bottleneck on a single computer when we need to serve, when we need to send a file across, right? So as you remember, a server has a single IP address that we basically look up for. It's like we want a particular server, but then here we do not know the location of all the different peers in the network. Most of the most of the application, the peer-to-peer application you would know are basically the most popular one is BitTorrent, where you basically exchange files in a network, in a peer-to-peer network. Um, there's a bit of legal stuff about what you can share in a peer-to-peer network, especially BitTorrent. But then that will be basically out of the scope of this lecture. You have some other applications, and one of the other one you might know as well is Microsoft Teams, or as known as Skype, right? So we have different networking architectures, right? And the well known here is the client server application. So the client server application, as you know, you have a server, right, that basically has a file, the file that we want to share, right? And then we have the different clients, right, that basically share everything in a network, right? And each and every client has basically its upload rate, right? A download rate, and then they all want the file. So U sub s, that will be the upload, like the upload rate of the server. U sub s, that's the upload rate of the server. U sub I is the upload rate of any given client, right? And D sub I is the download rate of any client. In this instance, we have client 1 through client n, right? So this is basically what I was trying to explain here. D sub I, the download capacity of the user I, and the U sub I is the upload capacity of the user I, right? That's basically what we would use. We'll be doing a little exercise trying to see how long time does it take to download the file f, right? Given the architecture we have. Like, we'll be comparing two architectures here, the client server architecture and the peer-to-peer architecture. Starting by the client server architecture. Remember that the client server architecture has two main components. The client on one side, right, that basically waits for the server, the client on one side that makes the request to the server, right? It speaks to the server, I would like to get something, right? And the server on the other side that basically waits for the request from the client to basically give a file or a page to the client, right? And it's only and only the server that can provide those type of services, right? Okay, so in this instance, all right, so in this instance of a client server application, what we will do, we'll basically what we want to calculate the distribution time. So this is the time that a file F leaves its location to all the different other clients, right? That's the distribution time. And what we will be doing in this exercise is to calculate the minimum distribution time during the transfer of a file F from a server in a client-server architecture to the client, to both architectures. That's basically what we'll be calculating. So we have the server transmission. So the server is just sending files to the client. This is very sequential. This is a client-server application. So if we have n clients, then we'll be sequentially sending the file to each and every client from the server, right? So the time to send one copy, obviously, is the size of the file, right, divided by the upload rate of the server. So imagine that you have this server and then you want to send a file to this particular client, right? You have this server, this client can only can at least download this file at the speed of its download, right? And also at this particular time. The particular time here is the file size divided by the upload rate, right? This is the minimum distribution time for a particular user I, right? But then there are multiple other constraints that basically dictates this distribution time. Sorry about that. And then if we have n users, it's basically that particular entity, like the distribution time to send to one computer multiplied by the number of users in the network. So we have this other quantity. That's the reason why you have those two here. But then in the worst case scenario, for those who are doing the complexity analysis with the big annotation in extension, then we're speaking about the worst case scenario. What if we have n users? Then the distribution time from the server to those n users is n times the distribution time to send the file to one user. And these are the formulas that you need in a client server scenario, right? Just remember that as it is. Now we have the clients. On the client side, we have the download rate. So what is the download rate needed for me to get the file within a specific time t, right? So the download rate also can be a bottleneck because the upload rate from the server can be very fast, but then your download rate can be very slow. So whatever speed this upload rate is, if your download rate is slower than the upload rate, obviously you will be creating a bottleneck on your side. Remember the previous lectures, what we were doing about the transfer between the different client server, client, with the different networking medium that can link them, right? So the download time from the server to the client, given the download rate, is basically the file size, right, divided by the download rate. Will give you as well the minimum client download time, for the client. Okay, now given all that, right, we have now some components here. You have to take note that this is the distribution time in a client server architecture right? This is the minimum distribution time. So here we're calculating the minimum distribution time. In a client-server architecture, this is the lower bound of this distribution time, right? And remember, this is the maximum. This is the worst case scenario you can have. If you have n computers, what's basically the time, or the distribution time, or the time to send that file F, right, to all these clients. And what is also the bottleneck per client based on their download time. So the distribution time in a client server architecture will be the maximum of those two, right? That is the maximum of those two. That will be the distribution time, the maximum, because if one of the different factor is greater, right, or let's say one of the different factors, right, brings these one of these components to be high, means that the time for the server to send something to the client will take longer. For example, if this computer, for instance, this computer has a downloading rate that is very, very small, then because of this guy, right, the distribution time for that particular file to all the computers, all the other computers might have the file except this one, because this one will be still downloading the file, right? And it will be still downloading the file because they rely on this particular server, right? That's one thing. That's not on the downloading time of this particular computer. But then there's also another problem. Remember that this is the server. The server contains this file, and all these computers rely on this server, and all their requests are going through a router. It means that if they all send the request to the router, this guy can be now the bottleneck, right? It can be the bottleneck in the sense that all the requests are going there depending on the routing algorithm. Then you might have a little delay sending the file and receiving the file. So you need to be careful when you are basically employing this type of architecture. Okay, as the next slide is the next couple of, this slide will be basically explaining you how this all of the client server architecture works. As you can see, this particular portion grows proportionally to the number of computers in the network. It grows, in fact, linearly. So if you have this n here, you take as your function y equals ax, right? Where your x can be your f divided by us. Because of this a, right, which is the slope, you can see now that we have a linear function. Okay, assuming that a is positive, here we have a positive number, so it will linearly go upwards. So the more computers we have in the network, the greater distribution time we'll be having in the network as well, in terms of distributing the file. Now the peer-to-peer application. The peer-to-peer application, as we mentioned, remember we don't have too much of a difference, right? When you look at this picture and you look at this picture, no, not too much of a difference. We have a server. We have a server that has the file that all the clients want. They're all looking forward to having that particular file, right? They all want to have a piece of that file. But then let's assume that that file, we know that a file is divided into pieces of bits, right? They all differ, they all have bits. And then for like in the client server application, it will send that file as a block to all the different users, right? So the server transmission must upload at least one copy. So what it does, instead of saying, okay, we have 1, 2, 3, 4 computers, right? And then the client server is saying, me alone as the server, I'll send the file to all the other clients because they do not speak to each other. They do not even know that they exist. The only thing that exists to them is the server. But then in a peer-to-peer application, we need to send the file at least to one client, right? Which means that, let me get rid of all of this, which means that, okay, I want to keep at least the representation of the file in memory. So if I send this file to this client, I'll be having another file here. What does that mean? It means that in a peer-to-peer network, we have this computer and that computer that now have the file. Now the client, on the client's point of view, the client must download the file from the server, right? It must download the file from a server, or it must download the file from the computer that has the file. And the computer that has the file in this instance is the server. The computer that requests the file is the client, right? Now all the clients, because remember it's a community, right? It's a community of things. They aggregate, like all the client as aggregate must download the number of the file bits. Remember the way I broke down the file into different bits, right? That's basically that. So it basically downloads, the clients downloads all the bits, right, from all the users to get the file, right? The clients, the different other clients, downloads the file from the other clients. Like you see, this server has the file. Fine by everyone else. But then this computer has also the file. But then let's assume that this one wants the file. So it says that n, which is the number of users is the network, as aggregate must download n file bits. So we need to get all the bits, right, from from the users, right, to get the particular file. Let's say this file has 5 bits, and we have 5 bits here, we have 5 bits here, right? Or let's say we have 3 bits, and here we have 4. It means that this guy will just take 1 bit from this computer, and this guy will take 1 bit here because it misses 1, and it will also take another bit here or there, because this basically a centralized way of how the peer-to-peer file sharing procedure works. It's much more complicated than this, but then you have an idea. If this one has the full bits that constitute this file, these guys will take the different bits to make up the file. If obviously this only one makes the request, you'll download the whole file bit by bit. But then if this guy makes the request to get the file, then there is a particular guy says, you know what, these guys, they have the file or they have pieces of it. You can download it from all of those guys. So take it from this guy, take it from that guy. Yeah, everything is just take it, like the file is here, the file is here, the file is here. And there is a computer here, call it imaginary, don't call it a server, saying that this guy has a file, this guy has a file, this guy has a file. So it won't just download from this guy. That will be a client server application. So you'll take it from here, and from here. So this, it makes the request, and all those guys are saying, there you go, we're giving you the file. and all of these guys have an upload rate, right? And then you do the addition of the upload rates to see um, your different the way the time that you'll be getting to get the file. Given that your upload rate is equals to their upload rate is equals to your download rate, right? What did I say? Their upload rate is equals to your download rate. Then you'll be literally downloading as they upload. Let's say your download rate should be basically greater or equal to the upload rate, then it will make sense. Now we go then to this particular formula, right? Cool. There you go. Now, what do we have? We have basically the distribution time in a peer-to-peer application, right, has a lower bound, which is this. And if you look at it very well, you would see that it's most of the time lower than it's most of the time lower than the it's most of the time lower than the client server application, right? Now, why am I saying that? So here, what do we have? We have the time to send a file from one computer to at least another one. Remember, the client server application, we are having a linear growth of this particular entity, but then he's at least one user. So this is one constraint, right? And then we have the same thing here on the other side, which is the file divided by the download rate of the least download rate of all the computers in the network. All right, no change about that, because we also saw that from the client server part. But then now this is the brand new one. Let's just clear the screen just for the last one. The last one is it's fairly interesting in the sense that we have the number of computers in the network, right? We have the file size, right? And then we have the upload rate from this from the server, right? My handwriting, open quote, right, in double quotes here, because it's a server, it's the computer that's basically has the file and send it. And then we have the upload rate of all the other computers in the network that do have the file. But so does this at each peer bring the service capacity. So if you have 10 computers, if you have like the summation of all the other um, uh, upload rates in the network of the different computers that actually do have the file. Very, very, very important. Let me clear this, right? Um, Let me clear that. So this is the formula, and I will not write it down anywhere else again. This one, very important for you to calculate the distribution time in a peer-to-peer architecture of a file in the network, right? Is there any bottleneck? There is, sure. There is. If some files are withdrawing from the net, I mean, it's not really a bottleneck, but then it's much more like a little trouble. If some computers are withdrawing from the network, if some computers are shutting down. Nevertheless, there are some other computers that will be still on, and they'll avail themselves to give you a piece of the file, right? So basically, that's the nice thing in here, and that's very interesting. All right. So here you have a use case, right? Here you have a client that has an upload rate of U, right? The file size divided by the upload rate, which has a time client to server of 1 hour. The upload rate of the server is 10 times that the upload rate of the client, and the download rate, the minimum download rate is greater or equal to the upload rate of the server, right? So as a question, that I will ask you in the quiz, what is basically the time? What is the minimum distribution time of a client server application, right? And the peer-to-peer application when n, speaking about this guy, when n equals 15. Okay, when n equals 15. All right. What's the minimum distribution time when n equals 15 for both of them, right? For both of them, when n equals 25 and when n equals 35. So in fact, we'll be having 4 of them. When n equals 5, when n equals 15, when n equals 25, when n equals 35. What is the minimum distribution time, and what do you see about that, right? All right. Okay, so basically we done with the different architectures and the examples that that we have about the distribution time. So now we'll be going to something that most of you must know. It is BitTorrent. So BitTorrent, right, is one of the most famous peer-to-peer application that we use on the web, right? So the peer-to-peer, or sorry, I would say the BitTorrent application makes available computers in a network in a peer-to-peer architecture. And the most important part in the BitTorrent network is what we call a torrent file. And I'm sure you heard about what we call a torrent file. So basically, you're looking for a file, for example, a Linux image. That one is legal because it's free. I'm not speaking about an MP3 that has some copyrights in it. So I'm talking about a Linux file that is basically free to download over the web, right? So when you want a Linux file, you're basically downloading a torrent file. So you will not download the ISO file, you download the torrent file. When you download the torrent file, what the torrent file does, it's basically a set. It's basically brings to your computer a copy of the tracker, right? The tracker tracks the different pairs of the participating in a torrent, right? And each and every of these computers tracked by the tracker, they have the piece of the ISO, or let's say the image of the Linux file, right? That's the thing. And the file, right? The file is divided into chunk of 256 kilobytes. So if the file is some couple of gigs, it will be divided into a couple of bytes, and those bytes will be 256, and each and every pair will be having a couple of those chunks in the system ready to be shared, right? And let's assume that you are here. You just came into the family and then say, okay, guys, I'm looking for people who have the Linux ISO. And this track, oh, sorry, the torrent file that basically contains the tracker, a copy of the tracker will basically tell you which computer are closer to you so that they can share those things basically quicker. Right. All right. So what happens is like Alice comes and say, okay, cool, I'm looking for the file. And what Alice has, she obtains the let me clear this thing up. She obtains the list of the peers from the tracker, right? And what it, because we assume that you already downloaded the torrent file. The torrent file has a copy of the tracker, right, which is the list of the other peers that are participating in the distribution of that particular file, and they all of them has some numbers of chunks of the file. And then she begins exchanging the chunks in the network to get the final big chunk that would make the file. So let's assume that Alice here, right? Let's assume that we have 10 chunks, and computer 1 through computer n have they all have the chunks, right? But then she can get chunk 2 and 4 from computer 1. She can get chunk 5 and 7 from computer 2. She can get chunk 1 and 3 from computer whatever. She can get chunk 2 and 9 from the other one, and then she get chunk 8, and she does the reassembly of all of that from all these other computer. Then you have 1 2 3 4 5 6 7 8 9, right? Instead of having a single computer here that will be calling the server, and then she'll speak to the server, say, okay, you know what, that big file that is about 2 gigs, can you please send it over? And then it will take days to download it, while here it's going to each and every computer to say, give me a little chunk of that file, and please guys, I'm looking for the fastest of one of you so that I can get the file faster. I mean the chunks faster so that I can make the file quicker as well. So that's basically BitTorrent in a nutshell, right? So what also happens is that you have basically your some algorithms here, right? But before even going to the algorithms, we have the policies around the BitTorrent community. So when you join in the file, right, when you join in the community, you do not have any chunks. Obviously, you have nothing, right? You just get in there and then say, okay, hello guys, I just came in here, and I'm willing to share some files. But then now you're getting files over time, you're getting registered into the tracker saying that I'm a particular user in the community, and then I'm willing to share some parts of the files, right, to my different neighbors or to the different peers, right? And what happens is like you now download chunks from the other people in the community, and in the meantime you also upload some chunks that some other people are requesting from you, right? That's the thing. So that like you just get in it, and then you make it available to whoever needs that. But then there's a problem here. Remember, the peer-to-peer architecture is as best as the number of peers in the network. Like the bigger the number, like if you go back to the formula here, the bigger the number is, right? The smaller, like the bigger the number is in terms of this, the smaller the distribution time will be. But then if the network is small, then you'll end up being in a client server architecture, almost to the worst case scenario where you have one computer which will act like the server, and one computer, which will act like the client. So here we go to the churn. Like, let's say, like we all do, I'm sure, I mean, most of us, you go to a peer-to-peer network, you get your file and you disappear. Selfishly, you go away with your file, you get rid of your identity in the tracker. You say, you know what, guys, I'm not part of this community anymore. I got what I wanted, so bye, I'm leaving. Don't worry, there's nothing really bad about that because torrents have BitTorrent or peer-to-peer communication in this particular file sharing structure. They basically also have a lot of bets. We'll be speaking about that a bit later. Now, in the torrent building of things, right, there are two sorts of protocols, discussion topics. We're speaking about requesting some chunks, right, and sending some chunks. We'll be speaking about the tit-for-tat later. So you request some chunks, right? Basically, when you want, like, remember, you just come into the community. What you do is like you asking for a file. You're asking for some files, right? And you obviously do not have the file. So what happens is, like, remember when we were doing the downloading from the chunks, from the downloading of the chunks from the different computers, what you do is like you taking some two chunks at the first time, and each and every chunk they have 256 kilobits, right? If you take chunk 2 and 4, then you're missing a couple of other chunks. Remember that to say there are 10 means that you're missing 8 of them. So you will be requesting the missing chunks from your different partners. But then there are some couple of algorithms of looking for the chunks. You don't just look for them. There are multiple algorithms that are there for that. But then the most common one is the rarest first. So remember, there is no server per se, but then there is a central computer that would say, okay, I have a bigger look of everything on this network. And then you can look for the chunks into your straight neighbors' computers. And then you can see in your neighbors' computers that the chunks that I'm looking for is not very well, it's not all over the place, right? So get what not everyone has, make it available to yourself means that you download it and then you redistribute it so that it doesn't get rare anymore, and then you keep on doing that until everyone has all the chunks. Right, this is almost like Robin Hood, right? You take from somewhere and then you just distribute for free to everyone, right? This is one thing when we're speaking about requesting. Now, when it comes to sending, right, you have your file, and then you would there are some couple of algorithms as well that are there for that, right? We're speaking about unchoking, for example. That's basically one part. So once, like, let's say we have two separate networks, right? That basically require one set of network. Uh, have they basically have some chunks, and then the other set of network has the complementary chunks. Means that they are choking. They can't download everything. They're missing uh, 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 the missing chunks. So what we do, we have like you see the other peers are choked, right? Because they do not receive anything, and she cannot even give anything. So what we do we have to select some other peer around yourself in the new network to make sure that we unchoke the network. Remember, it's a community. We're all holding hands, we are all helping each other. But then if you can't do much on your side, you can't help the community, right? It will be better in the picture. Let's us like this is it. So we are here in the network. This is one network, this is another network. And as you can see, there's a bidirectional communication between each and every peer, right? Means that everything is being shared. But then they all want to speak to you, and here they all want to speak to you, right? So, but then let's assume that here is Alice and here is Bob. And Bob is being choked, right? Bob is being choked because he doesn't have any data, or he doesn't have the other chunks that the other computers are requesting. This is an issue. But in this other group, they do have that chunk. So what happens? Let me clear all of those. Let me clear that. What happens? Alice then basically unchokes Bob, right? It means that this computer can now get the the next set of chunks that it was missing by Bob to Alice's group, right? So because of that, Bob has some providers here, right? And Bob has some providers, and Bob as well is their provider, right? But then by doing so, then Alice also becomes, let me clear this, Alice also becomes one of the providers of Bob, right? Because Alice helped Bob, right? And also Bob becomes also one of the provider of Alice. So remember, this is helping. They're helping each other, right? This is very, very important. But then what they do, they basically, you also have that other algorithm that makes sure that uh, they're looking for different peers that has the highest upload rate so that they can download things faster. When I'm saying downloading things faster, given that their downloading rate is higher than the highest downloading rate, means that we have a smoother conversation in between. And just for your information, it might not be full in the extent, but tit for tat means that if you help me, I'll help you. If you do not help me, then we compete. That's basically that. But in this instance, because Bob helped Alice, Alice is also helping Bob in the sense that if I have a file that you do not have, I'll give it to you. That's basically it. That's done for this particular lecture. You'll be having a quiz regarding everything we spoke about here. Remember that one question of the quiz will be based on one graph here that we spoke about. Okay, guys, see you on the next lecture. Bye.